Hello everyone, welcome to my presentation. I'm Chuan Guo from Illinois University, Edwardsville. Today my topic is on periodic motions of a moving car pendulum system. For this presentation, I will start with a physical model introduction. Then I will introduce the implicit mapping used to solve this physical model. Stability and bifurcation analysis is based on the implicit mapping. Then I will show the periodic motions obtained from this method. Numerical simulation will also be shown to compare with our semi-analytical results. Finally, I'll wrap up the conclusion. So this is the physical model. We can see a moving car with a spring and a damper is driven by a periodic excitation force, and the mass is connected to the moving car with a massless part. So this is a typical moving car pendulum system. This equation is obtained by the Lagrange mechanics. This x1 means the displacement of the car, which is x, and this x2 is the displacement of the pendulum, which is theta. And here we use an implicit mapping method for this system. An implicit mapping is built here. We use for consider a pure M motion. We discretize it into mn points from the mapping P. The mapping P has mn parts from P1 to Pmn. For each step Pk is from the k-1 term to the k term. So this is each step of the mapping. The set of discrete points on the periodic motions for this system can be obtained for function gk equals to 0. Gk is a function of displacement, velocity, and parameters, such as this spring constant. And for periodic motions, we also have periodic conditions. Here x0 equals to xmn plus 0 to k pi. This 2 k pi is because of this is the angular displacement. And for y0 equals to ymn, this is the periodic condition. Then based on the implicit mapping, the algebraic equation for the periodic motions we obtained, we have totally 4 equations from G1k to G4k. For stability and bifurcation, we linearize the equation of gk equals to 0. Use this equation, we can define a new vector z equals to x and y. So this is the total result for displacement and velocity for all the displacement and velocity. Then delta zk equals to dpk times delta zk minus 1. Delta zmn equals dp times delta z0. dp is the multiplication of dpmn all the way to dp1. And dpk is a function in the matrix partial zk over partial zk minus 1. In this kind of way, we can totally get partial zmn over partial z0, which is this equation. This is the matrix dp. Then the eigenvalues of the dp matrix, we can, for the periodic motions, compute in this way, it's a 4x4 matrix. If the magnitude of all eigenvalues are less than 1, the PR solution is stable. If the magnitude of one eigenvalue is greater than 1, we say it's unstable. There are also boundaries between stable and unstable periodic solutions with high order singularity. This gives bifurcation, and also stability conditions with high order singularity. The bifurcation conditions for periodic motions, they have 3 cases. If one eigenvalue is equal to 1 and the other eigenvalue within unit circle, we say it's the seasonal bifurcation. If one eigenvalue is equal to -1, and the other eigenvalues within the unit circle, we say it's the pure doubling bifurcation. If the magnitude of a pair of complex eigenvalues is equal to 1 and the other eigenvalue within the unit circle, we say it's the Neymark bifurcation. Then based on these things, we can see the bifurcation tree here. This is the bifurcation tree for periodic node displacement x2 and the periodic node velocity y2. The black solid line means stable solution. The dashed line means unstable solution. This S means symmetric, and this A means asymmetric. We can see for these motions, we have started from in the omega range 0 to 15. There is a stable symmetric P1 motions to asymmetric P1 motions, then to asymmetric P2 motions. There are also asymmetric P4 motions in this way. And later also in this pure doubling, there's also P2 to P4 motions, and later have P4 to P8 motions. This is for the velocity case is the same bifurcation conditions with the displacement. The approximate expression for periodic motions is determined by the finite Fourier series as this function shown. Then the harmonic amplitude and the phases for periodic M motions can be expressed by this way. We get the amplitude and phases the frequency A0, BK or M, and CK or M can be achieved by these three equations. And here we show the harmonic amplitude A0 for the thing. This A10 means the harmonic amplitude for displacement x1. This is A20 is the harmonic amplitude for displacement x2. You can see here for x1, for A10, the values is very small, but for A20, the values are kind of large. This peak, there's a peak here. This peak is around 5, which is the natural frequency for the moving car, for the car system. And this is a very small peak here. This is influenced by the pendulum. This is for A0. And for A1, you can see here, for the A11 terms, the values is much larger than A0. This is the main term for the x1. For the x1 term, the main term is A1. And for P1 motions and P2 motions, you see there, the lines is very close. So this result is very close. For the harmonic amplitude A21, we can see the bifurcation here is much clearer. They have quite difference between P2 motions and P1 motions. This is harmonic amplitude A2. A2 should be similar with A0. For A2 here, the small peak is in the A1 just disappeared, and this peak is also close to 5. The values is compared to A1 is quite small, but already still very larger than A0. That's because the equilibrium point is very small. This is harmonic amplitude A3. We can see here for A23, the shape is similar to A21, but for A13, the shape is quite different with A11. This is because the values, you still remember that for A11, the value is around 1, but for A13, the value is already very small, to the 10 to the -2 this degree. So this means these terms make a little contribution to the displacement change for x1. And this is the last term we use for harmonic amplitude. This is A37 because the values already decreased to 10 to the -16, and it's already very small. And the bifurcation condition, is still similar. Yeah, and so here, and the maximum value is around 10 to the -4, but the minimum value is already very small. So we choose this term as the last term, which means if you want to use a harmonic balance method to represent this system, you only need 1737 terms. You can get a very accurate result. So we use this harmonic balance, we use this way to this harmonic amplitude from A0 to A37 to get the numerical simulation result. Shown here, the black solid line shows the numerical result, and these circles, these red circles, is our semi-analytical result. Here is the IC means the initial condition. We can see here is the symmetric pure 1 motions at omega is to 11.18, and it's a symmetric case. This is for x1, y1. This is for x2, y2. The physically, you can see here the fast changing area and the slow changing area. This is for P1 motion. And here is the asymmetric P1 motions at omega is to 9.65. Yeah, the difference is not too much. The shape, they are still in this area, in the small, in this area and this area is still the slow changing area, the fast changing area, similar with the symmetric P1 motions. The only difference is this one is asymmetric, and this x1 and y2 is same. And here is the asymmetric P2 motion at omega is to 9.65. This is very close to the pure doubling bifurcation point. So you can see here that there have 2 loops. These 2 loops is very close because this point is very close to the bifurcation point. The shape is very similar to the asymmetric P1 motions because their omega value is very close. Okay, here is the conclusion. The bifurcation tree of a moving car pendulum system was obtained. The discrete periodic nodes of a periodic motion were obtained from the implicit mapping. The corresponding stability analysis and bifurcation analysis of the periodic motions were performed. Numerical simulation of the stable periodic motions were complete from the analytical tree.